1 because the first position bits are same, but the second position bits are difficult. Dissimilar. So that's why the Hamming distance is 1. But and also weight of the B. So B I'm taking 0, 1. So weight of the B is also 1 because what is the weight? Weight of the bit. Weight is I'm already told you. I just already told you that weight is basically the number of the 1 present in bit sequence. That means number of the 1 present is 1. So WB equals to 1. So Hamming distance equals to 1 and WB equals to 1. For this also, the Hamming distance is 2. That means 0, 0, and this is B equals to 1, 1. So Hamming distance equals to 2. And the weight of the B, that means B is 2 because there is 2 number of, that means 2, 1 present at this B. Okay. So that's why the weight of this B is 2 and Hamming distance between these two is also 2. So you know that I'm taking A as 1, 0, 1, 0, 1, 1. So and B as this. So you can say, so this is another example. So this is not a linear. Okay, so when I'm taking A as 0, 0 and I'm calculating any Hamming distance with respect to 0, 0, all 0 bit, then the code sequence will be called as linear code. So but here it's a non-linear code like 1, 0, 1. Here also the dissimilarities, number of dissimilarities is basically you can see 0, 1, 1, 0, 0, 1 and 1, 0. So 4. And also the weight of the bit is also 4. So this is one example. But the thing is that the generalized thing is that when you consider the code is linear, that means for the linear code, the Hamming distance will be calculated with respect to all 0 code, right? So when the code is linear, it is sufficient to determine the distance between any code vector and all 0 vector, which is in the end the weight of that code vector. So that is the generalized point, that when the code is linear, that means I have already told you that when any Hamming distance is being calculated with respect to all 0 code, then the code is to be considered as linear code. So when the code is linear, that means this is 0, 0, 0, this is 0, 1, 0. So this is a linear code. So for this you can see the Hamming distance is equal to the code weight of the second code. Okay, second code sequence. So that is the thing. So here it is written that when the code is linear, then it is sufficient to determine the distance between any code vector and the all 0 vector. That means distance between any code vector and all 0 vector, which is basically the weight of that code vector. That means the second vector, which is considered as any code vector. Okay, so that is a generalized form. But the thing is that why we are bothered so much about calculating the minimum Hamming distance. So what is the significance of calculating the minimum Hamming distance? So what is the purpose of Hamming distance? So it's basically to correct the error correction purpose, actually error correction purpose and error detection purpose. So there is two things, error correction and error detection, and we will come to this later. So first of all, almost all the convolutional code, the practical use are linear. So the minimum distance of the code can be determined by finding the code sequence of the minimum weight. That means it is written that almost all convolutional code of the practical use are linear. Okay, so minimum distance of the code can be determined by finding the code sequence of minimum weight. Okay, so if we calculate the minimum code weight, so that will be the minimum distance. Okay, so this is considered to be same, that when I'm calculating the minimum weight, when we find the when we will find that the minimum weight of any code, so that will be the minimum distance, because the distance is being calculated with respect to all 0 code. for the linear code sequences, because convolutional code, almost all convolutional code of the practical use are linear. So the minimum distance, minimum Hamming distance of the code can be determined by finding the code sequence of minimum weight. Okay. So from the previous example, I'm just telling you that. So this is the linear code, and you know that the minimum Hamming distance will be 1. Okay, because the Hamming distance, the minimum Hamming distance will be equal to the weight of the code, any code, which the Hamming distance is being calculated with respect to all zero code. Okay, and the weight of that code is also 1. So we have to find only the weight of the code, and that will be our minimum Hamming distance. Okay, so that is what I'm trying to say. Now the question is that why we are bothered about calculating the minimum distance of the code. What is the significance of this minimum Hamming distance? Okay, because one of the most significant parameters of the error correcting or error detecting. Okay, there is two terms, one is error correcting and one is error detecting. What is the minimum distance of the code? So basically, when I'm finding the minimum distance of between any two code, then we can tell, or we can calculate the how many error to be detected and how many error to be corrected. Okay, so we will determine minimum distance of the linear code by state diagram and code release diagram. So first of all, what is the significance of the minimum distance or minimum Hamming distance? Is basically for the error correcting purpose and error detecting purpose. So significant parameters of an error correcting and error detecting code is the minimum Hamming distance of the code. Okay, so that is the significance of calculating the minimum distance of the code. Now we will see the procedure, the two procedures to calculate the minimum distance of the code. One is state diagram and one is code release diagram. So this is very easy. So we will see, we have already seen that what is a state diagram. We already discussed what is state diagram, but here we will modify it. A little bit modification will be there. Okay, I will see you. I will show you that there is a modified state diagram. It's called the modified state diagram. So let's go to this. So from the state diagram, it's called modified. Why this is modified? We will see it. This is called modified state diagram. So what modification is being happening here? So this is our traditional diagram. So first of all, let's go through this. What is written? The distance properties of the convolutional code is obtained by modifying the traditional state diagram in such a way that the modified diagram starts and ends in the all zero state, that is SA. Okay, so first of all, I'm telling you that we are considering the example as cconv 212. Okay, so 212, that means cconv 212, here also 212. So I'm taking this example, cconv convolutional code of 212 sequence. So the main thing is that in the modified state diagram, we will start from all zero state and we will end at all zero state. So in such that the way that the modified diagram start and end in the all zero state. So that is my intention. So that is my target. Okay. So keeping in mind this point, this is very important point, that the modified state diagram will start and ends in the all zero state, which is SA. So from the previous lecture, I'm just going to the previous lecture. So this is our previous lecture. This was our previous lecture. So just let me erase it. From this previous lecture, you will find in in your previous lecture